Hi, welcome back. So this drug on the left, molnupiravir, is an anti-COVID-19 medication. So this is the COVID-19 virus. And this is a very helpful medication, antiviral medication. It's used to inhibit the progression of COVID-19 disease. The original synthesis involved 5 steps and involved a lot of waste of solvent. The manufacturers Merck won an award in 2022 for developing a greener synthetic pathway with only 3 steps and a 1.6-fold increase in percentage yield. So this lesson is all about sustainability of the production of chemicals. And in this lesson, we're going to look at percentage yield and atom economy of single-step and overall reactions, and consider green chemistry principles of renewable feedstocks, catalysis, and designing safer chemicals. Okay, the first thing we're going to look at is efficiency of reactions. And we're going to look at a really important concept with green chemistry called atom economy. In order to produce more sustainable chemicals, we also aim for a very high atom economy. And percentage atom economy is defined as the molar mass of the desired product. And in the example we've got here, butyl ethanoate is our desired product, divided by the molar mass of all of the reactants. So in the example we've got here, we start off with ethanoic acid and butane-1-ol. We divide the molar mass of the desired product over the molar mass of the reactants, multiply by 100 to get a percentage. Ideally, we want to produce products with 100% atom economy because that means there's no waste. But in reality, that's not always possible. And we learnt about efficiency of reactions before when we studied equilibrium systems. So to go through an example, if we want to work out the percentage atom economy of the desired product, which in this case is butyl ethanoate, then we get the molar mass of the desired product divided by the molar mass of all the reactant atoms. So the molar mass of CH3COO, CH2, 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 CH3, the molar mass of ethanoic acid, and the molar mass of butane-1-ol times by 100. So that ends up being 116.0 grams per mole divided by 134 grams per mole times 100 is 86.6%. So that's a relatively high atom economy. Often we're aiming for 100%, so it's lower than that. Percentage yield is another way we can measure efficiency of reactions. And in order to produce a more sustainable chemical, we also aim for a high percentage yield. And percentage yield is defined as the actual yield divided by the theoretical yield from stoichiometry times 100%. So in an example, if the actual yield that we obtain in a reaction is 2.341 grams of the desired product, but our calculations of stoichiometry tell us we expect 5.869 grams, then we can calculate the percentage yield by dividing the actual yield by the theoretical yield, multiplying by 100. So if we sub in those values, 2.341 grams divided by 5.869 grams, the units cancel out, and we're left with 39.89%. Now, this is to 4 significant figures because both of our input data points had 4 significant figures. So always check the calculated result is to the correct number of significant figures. Then we need to think about reasons why we might have low yield. So it could be that reactants or products are somehow lost throughout the experimental process. A very real consideration is that, as we know, equilibrium reactions do not always proceed to completion. We might have a very slow rate of reaction. We might have impurities present in the initial reactants. We can have side reactions occurring, resulting in the formation of different unwanted products. And when multiple steps are involved, then we can have a multiplication of inefficiencies through those intermediate steps. So if we've got a percentage yield of multiple process steps, which often we have, synthesis of organic chemicals, what we can do is convert our percentages to decimals, multiply the decimals, and then convert the final answer into a percentage. So if we go from A to B to C to D, and the percentage yield of the step A to B is 70%, and then step B to C is 80%, and then step C to D is 65%, we can multiply 0.7 by 0.8 by 0.65 times 100 equals 36%, which is quite a low percentage yield. Now we'll consider some green chemistry principles, which we've come back to throughout this course. So first of all, renewable feedstocks. Renewable means capable of being replaced by natural processes within a relatively short period of time. So one of the problems that we have at the moment is that we have plastics that are made from fossil fuels, which are non-biodegradable. So the use of renewable feedstocks can be used as alternatives to using fossil fuels as a feedstock in the manufacture of plastics. For example, lactic acid occurs naturally in many organisms, including in humans. It can be obtained by the fermentation of sugarcane or cornstarch. Polylactic acid is formed from the condensation of lactic acid monomers. So here we've got a monomer of lactic acid. It's an equilibrium reaction, and here we've got our polymer of polylactic acid and water. Being a condensation polymer, it's reversible, this reaction. So polylactic acid can be used, for example, in the manufacture of medical implants, and it can remain intact for up to 2 years post-surgery during the time that the body heals, and then can be hydrolyzed and removed from the body. So it contributes to a circular economy. Now moving towards the future of more sustainable biofuels. If we use renewable feedstocks, there are several generations of feedstocks that we can consider. So currently we're in the first generation and second generation. So the first generation are using edible crops such as corn and sugarcane, for example, to make polylactic acid. We can have trans-esterification under alkaline conditions. The advantage is it's renewable feedstock, but a disadvantage is that the land that's used to grow the feedstock could instead be used to grow food, which is a problem when we don't have enough food to feed everyone on the planet. The next generation, second generation, is using non-food crops and waste materials, including household waste. So the chemical process could be, again, making biodiesel under trans-esterification with alkaline conditions. And there's less environmental impact compared to the first generation biofuels, which are using food sources. The disadvantage is the process used to convert that biomass, that waste, to liquid fuels is difficult. The next generation, the third generation, is to use algae and microorganisms. And they can grow in different environments, including in wastewater. It's a high productivity and potential to absorb CO2 from the atmosphere, but the downside or disadvantage is it requires extensive processing. And a fair way in the future, the fourth or emerging generation is to use cyanobacteria, which are engineered bacteria or cyanobacteria, and it's using green biotechnology to absorb the most CO2 and create lipid biofuels. But unfortunately, this technique is currently very expensive and is not conducted on a large commercial scale at the moment. Now, we've talked about catalysts before. Catalysts are very important in green chemistry. Some of the benefits of using catalysts in organic synthesis include improved selectivity, so minimising or eliminating unwanted byproducts, lower energy consumption, because reactions can occur at lower temperatures and pressures, the use of renewable sources of feedstocks so that we can use biomass instead of fossil fuels, safer reactions in some cases, reducing the risk of accidents and environmental contamination. And by swapping to more preferred catalysts, we can get a longer catalyst lifetime in some syntheses by reusing catalysts and reducing the impact of poison catalysts ending up in waste. Okay, so in the past, in organic syntheses, sometimes stoichiometric quantities of reactants were used that ended up as waste. So here's a case study. Jones reactant is a combination of chromium oxide and sulfuric acid. It was originally used to oxidise secondary alcohols to produce ketones. But the toxic chromium ended up in waste as this byproduct, Cr2SO4 bracket 3, chromium-containing waste. A greener pathway ended up with the same desired product, but just with water as waste. And that's by using a palladium catalyst that can be reused. And having water as a byproduct is much safer and a much better atom economy than having toxic chromium waste. So the catalyst is a water-soluble palladium-2 complex. Air is used as the oxidant. It was no organic solvent required, and the catalyst is recycled via phase separation. Okay, so another thing we need to consider is the design of safer materials and chemicals to begin with, leading to less waste. And an example is in packaging materials. So safer packaging materials are those that can be biodegradable and not persist in the environment. So condensation polymers, such as polybutylene succinate, or PBS, is produced from the reaction of a dicarboxylic acid monomer. So there's a carboxyl group here and another carboxyl group here, and a dialcohol monomer. And we've got a hydroxyl group here and a second hydroxyl group here. When these monomers are brought together and react, we end up with a polymer of PBS and water. And these equilibrium arrows tell us that this is a reversible reaction. So to make the polymer is condensation. The reverse process is hydrolysis, which means that we can go back to our starting materials and means that we produce less waste. Another growing area of designing safer chemicals is to use marine sources, in particular seaweeds, brown seaweed, red seaweed and green seaweed. These contain biopolymers which naturally occur, which are polysaccharides that aren't based on starch. And they include alginate, agar, cellulose, which is not, as we know, we can't digest. Another example is carrageenan. These biopolymers can be mixed and processed to produce bioplastics, which then have applications in packaging. And advantages of using seaweed: they've got a lower carbon footprint than other carbon sources. They can be grown relatively quickly. They're biodegradable. They result in less food waste. They're actually edible, and these polysaccharides are already used as food additives. And by taking carbon dioxide out of the water, they're contributing to de-acidification of the ocean, which is a good thing for the environment. There are other marine sources of mollusks, crustacea, fish, microorganisms, which can also be used to produce biopolymers that can also end up in packaging materials. Another thing that we can do with designing safer chemicals is to use safer solvents. Here we've got a part of column chromatography, and it's used to separate, this one's used to separate the colours in spinach. The original solvent that was used was dichloromethane, and in one example, dichloromethane and ethyl ethanoate are used as the solvent mixture. But dichloromethane is toxic and persists in the environment. A greener pathway is to use a safer solvent. So the greener method instead used a safer mixture of heptane and propantuol. Still got the desired effect of separating out the components, but resulting in a safer solvent that's used. Okay, sildenafil is a medication used to treat hypertension or high blood pressure. The manufacturers originally synthesised the compound using 1,300 kilograms of solvent per kilogram of medicine that was produced. A greener pathway resulted in recycling of solvent, reducing its use to just 71 kilograms per kilogram of medicine produced. Which statement is correct? Have a go at that question. Okay, let's look at each option in turn and choose the best response. Using less solvent results in more waste. That doesn't make sense, so that's not right. Solvents don't need to be considered in the use of green chemistry because they're not present in the final product. It's true they're not present in the final product, but in green chemistry we need to think about the whole process. So B is incorrect. C, a principle of green chemistry is to use processes which result in the production of less toxic waste. Yes, that is a principle of green chemistry. So C's looking good. And D, a principle of green chemistry is to use processes which result in a lower atom economy. We want a higher atom economy. So D is incorrect. Our answer is C. Okay, so we've learned a few equations, or a couple of equations. Percentage atom economy is the molar mass of the desired product over the molar mass of all the reactants, or all the products, times 100. The percentage yield is the actual yield obtained divided by the theoretical yield from stoichiometry, times 100%. Renewable feedstocks, the first generation which is currently available is using edible crops such as corn and sugarcane. The next generation is using non-food crops and waste, including household waste, as biomass. The third generation is using algae and microorganisms. And the fourth, or emerging future generation, is using cyanobacteria, which can photosynthesize. If we have multiple steps in the production of an organic chemical and they have different percentage yields, then the overall pathway is taking the percentage yield of the first step multiplied by the percentage yield of the next step by the final step times by 100 to get, in this example, 36% for the overall process. There are several advantages of using catalysts in green chemistry. They include improved selectivity, lower energy consumption, renewable source utilisation, safer reactions, and a longer catalyst lifetime. Next up is the progress check, and I'll see you soon. Bye.